Hello, this is Dr. Simon Romero, and I'm here to give you the video tutorial for section 12.5, Lines and Plane Space. In this section, we're going to cover equations of lines, in other words, a way that we can describe algebraically lines in the three-dimensional space. We're going to talk about parallel, perpendicular, and skew lines. Then I'm going to talk about angle between intersecting lines, then equation of planes, how to describe them algebraically, parallel and perpendicular planes, and then I'm going to talk about a little bit about angle of intersection of planes. Intersection of planes in general is going to be covered in our class activity next class. These are the practice problems. As always, I suggest you to do them all. Lines. If you remember, in 2 dimensions, a direction can be described by a single number. This is no longer true in 3 dimensions, so we will need a vector to describe a direction. The direction vector for a line is going to be a vector in the same direction as the line, and that as we show here in the picture. Let me just start a little bit of how we're going to create equations in order to describe points in the line. So suppose that we have a starting point x0, y0, and z0, and a direction vector that I'm going to call b, with components a, b, and c. So the thing that we're going to do is, our objective is try to find a condition that only points in the line satisfy. In order to find that condition, we just take a generic point in the line that I'm going to call x, y, z. Note that we have a combination between vectors and points, so we're going to try to do everything in terms of vectors. The vector r0 is going to be the vector that joins the origin with the point x0, y0, and z0, so the components are going to be x0, y0, and z0. We will do the same for the point x, y, z. We're going to have a vector that goes from the origin to the point x, y, z, and that's going to be the vector r. From here, the question is if we can find a vector equation relating b, r, and r0. The answer is yes. If we take a scale version of b, we can get this configuration. Notice that in this case, the thing that we're going to have is the vector r that goes from the origin to x, y, and z is the same as the sum of the vectors r0 and the scale version of b. r0 and the scale version of b. Notice that that gives you the equation r is equal to r0 plus d. Unfortunately, this is a vectorial equation, and remember that we're trying to describe points. So from the vectorial equation, the only thing that we need is we just put the components that, remember, they're very related to the points, and then we're just going to do the addition of the vectors. So the thing that we have here at the end is that this vector is equal to this vector that we have here. In other words, 2 vectors to be equal, the components have to be equal, so the x component has to be equal of both vectors, the y components have to be equal, and the z components have to be equal, and that gives us a set of parametric equations. These are what we're going to call parametric equations of the line. So the parametric equations of the line in the same direction as the vector a, b, and c to the point x0, y0, z0 are given by this. Why 3 equations? Because remember, we need, in order to describe a direction, we need a vector that requires 3 components. So if we want to find the parametric equations of the line, we need 2 things. We need a point in the line and a direction vector of the line. The point in the line goes here. This is our starting point, and then the direction vector of the line is just going to be stretched by the parameter in order to describe all the points on the line. The symmetric equation of the line is like this. I'm not going to talk too much about it because we're not going to use it that much. Let me better give an example. 2 points actually describe a line. So the question is, given 2 points, can we get the parametric equations of the line? And the answer is yes. Take the 2 points, and then in order to construct the parametric equations of the line, we need a direction vector. Well, it seems that the vector PQ is a direction vector of our line, so let's try to compute the vector PQ. The vector PQ is equal to 4 minus 2 and 2. So the line described by the parametric can be described by the parametric equations. Here is the point P, so remember we need only 1 point, and here are the components of our vector that's going to be of the direction vector of the line, and if we put them in this way, we get the parametric equations of the line. Let me talk a little bit about these parametric equations and what do they mean. Let me make some observations. Note that every point in the line can be described by a particular t. So if you give me a particular t, for example here, t0 gives you the point P, t1 gives you the point Q, and all the other t's give you different points that are in the line. So if you give me a t, this equation is going to give you the particular point. Also note that if I can pick a different point as the starting point, for example the point Q, and the thing that I will get is I will get the same description of the line. The only difference is now the vector B will be starting at the point Q. So the parameter will change now when we start at B, T1 describe Q. Now if you start at Q, then S equal to 0 will describe that point, and S equal to 2 will describe the point that before was described by 3, T equal to 3. Let me tell you parallel lines. So now that we have these equations, the idea is if we have two parametric equations of two different lines, can we tell whether they are parallel or perpendicular? And the answer is yes, by just looking at the only thing that you need to do is to look at the direction vectors. If the direction vectors are parallel, the lines are parallel. And remember that if you want to check two vectors are parallel, the only thing that you have to do is find if one is a scalar version of the other. Perpendicular lines, if the direction vectors are perpendicular, then the lines are perpendicular. Remember that in order to find if two vectors are perpendicular, you just take the dot product and verify that is equal to 0. Skew lines are lines that do not intersect and they are not parallel. Intersection of lines and angle between lines. Two lines intersect in a point, and the angle between two intersecting lines is equal to the angle between the direction vectors. So again, the only thing that you need to do if you are computing the angle of intersection of two lines is just computing the angle of intersection of the direction vectors. Let me talk about planes. Planes are two-dimensional objects in a three-dimensional space, and they are the two-dimensional equivalent of a line. A plane is determined by 3 points. We will describe the inclination of a plane by a vector. A normal vector of the plane is a non-zero vector orthogonal to every vector line in the plane. This happens to be a very nice way to describe inclination, because unlike in lines that you just have to give one vector that lives in the line, in a plane a lot of vectors with different direction can live in the same plane. But if you take something orthogonal to the plane, there is only one direction that can work, or the opposite one, but we're going to consider them as the same. So the inclination is going to be given by a vector that is orthogonal to every vector line in the plane, and that's the normal vector of a plane. So the question of the plane in space. So let me consider the point x0, y0, z0, and the normal vector that is going to give us the inclination. The normal vector n is given by a, b, c. So we have something like this. Now we take a generic point in the plane, and again we're trying to describe an algebraic expression that is can be only satisfied by points that live in this plane. So let's start. Now this case is simpler. Since a normal vector is orthogonal to every vector lying in the plane, we just need to get one of those vectors lying in the plane, and since x0, y0, and z0 is in the plane as well as the point x, y, z, the only thing that we need is to join those 2 points, and we have a vector lying in the plane. Therefore, the dot product of r and n has to be equal to 0. Unfortunately, this is a vectorial equation. Remember that we want to get a condition for points. So the thing that we're going to do is do the same thing that we did before. We put components and we distribute 2. We do the dot product, and the thing that we have is what we call the scalar equation of a plane. So if you have something like this, the scalar equation of a plane with normal vector a, b, and c to the point x0, y0, and z0 is given by this equation. So if we want to find an equation of a plane, we need two things: a point in the plane and a normal vector of the plane. The point goes in parentheses inside of subtracting x, y, and z, and the components of the normal vector are going to be the coefficients of these things. And remember, this came just from doing the dot product. So let me multiply through. If you multiply through, the thing that you obtain is something that we call the linear equation of the plane. So the linear equation of the plane with normal vector ABC to the point x0, y0, z0 is given by this, where d is just minus this thing over here. If d is equal to 0, then the equation describes a plane through the origin. Now this one is not as useful as this one is the way that usually we're going to encounter planes, but it's not the easiest one to get. I suggest you to get the scalar equation first, and then go to the linear equation. So, I wanted to tell you, notice that the components of the normal vector of the plane are just the a, b, and c, the numbers a, b, and c, that are the coefficients of our variables. So let me give you an example. Find an equation of the plane to those points over there. So we're given 3 points in the plane, P, Q, and R. And in order to find the equation of the plane, we need a normal vector of the plane. From the given points that we have, we can construct two vectors lying in the plane. Notice that these two vectors lying in the plane, in order to get a normal vector, we need a vector orthogonal to P and Q. And we know that the cross product is a normal vector of the plane, since it is orthogonal from both P and Q. So I'm going to take the cross product. Notice that I just put the determinant over there, and I obtain that the normal vector is 1, 1, 0. So finally we have a normal vector of the plane, and we have actually 3 points in the plane. So we just pick one. The equation of the plane will be this one over here. If we choose the point P, or if we choose the point Q, this will be. No matter which one you pick, when we take the linear equation will be the same. Parallel planes. Two planes are going to be parallel if the normal vectors are parallel, just like in the picture. Two planes are going to be perpendicular if the normal vectors are perpendicular. And the intersection of planes, every pair or non-parallel planes intersecting a line, and the angle of intersection is just going to be given by the angle between their normal vectors. And with this, we finish this video tutorial of equations of lines and planes. Thank you very much.